Okay, I will be solving problem 4 from the CFD midterm 1. So the goal is to transform this partial differential equation into the finite difference equation using the first order forward with respect to time and the second order central with respect to space. We need to find the truncation errors, if it's consistent, and whether or not it's implicit or explicit. So solving for the first order forward with respect to time, we are going to begin with the Taylor series expansion around the time step n+1 and n. And that will be the notation for through time, and the subscripts will be the notation through space. So moving on, we can rearrange using addition subtraction to solve to this line, and then solving for the partial differential, divide out through, cancel out the time terms. We have our first one. Now we have to solve for the second order central, and this is partial u partial x. So beginning with the Taylor series expansion around I-1 and I+1 and I have these terms. And if we call this one equation 2, equation 1, subtract equation 1 from equation 2, we can see a lot of these terms cancel out. And the same form as before, we rearrange and solve for partial u, partial x. And then we will be left with this as the remainder. And also note that this second order determines the order of accuracy we have. So this would be second order, and the previous being first order. One more time, we get to the Taylor series expansion. I-1, I+1, and the higher order terms. And then we expand all the way out to the fourth power. And adding 3 and 4, we can get to u of I-1, ui+1. And then we need to solve for the second order, the second derivative of u with respect to x. And then things cancel out once again, left here, second order accuracy. Cool, now we can take what we found, so partial u, partial t, partial u, partial x, second u, second x. Plug these in, and now we have our finite difference equation. Okay, in order to find the truncation error of that, we need to replace everywhere that we have something that is not ui of n, it's going to be replaced with its Taylor series representation. So we're going to begin with the u of t. This would be the first order derivative of u with respect to t. And these Taylor series would be the previous equations that we had. So wherever we had un plus 1 is going to be replaced by its Taylor series representation, and we have these terms here, and as you can see, this would cancel out here, t cancels out, and then we are left with this as our original derivative and plus some truncation, so we hold on to this for later. Okay, now we're going to do the same thing for the first partial derivative of u with respect to x. So we're going to go through, and all these Taylor series are the ones we've previously seen during the original derivation. So you plug them in, and then you can see these cancel out, cancel, go through, cancel, and then we are left with this at the bottom here. So we have our original derivative plus some other stuff, same thing. Okay, and do it again for the u with the second derivative with respect to x. Same thing, plug in the Taylor series, and a lot of this cancels out. It's very nice. It's partially from the second order accuracy, so that's good. So we see that again here, and then we're going to get all those equations that we just had. So we are going to plug them back in. So we're going to have you have u of t 1/2 delta t u second derivative t, and that same process continues for all the other terms. And then we can rearrange this into our original partial differential. So we moved the right hand side onto the left, what we had here, set it to the left side. And if this was going to be exactly the PDE, if we didn't have a truncation error, this would actually be equal to 0, but we do not. So this is our truncation error and our original PDE. And then we can also see that we have the first order accuracy and second order accuracy with respect to t and x. Okay, so to determine if this is consistent, let's imagine that we take an infinite amount of data points, and in order to do that, we would be shrinking our discretization. So as the number of grid points goes to infinity, our delta t and delta x would approach 0. So we can go ahead and plug those in to the truncation, and 0, 0, 0 equals 0. And by definition, the finite difference equation is consistent. Okay, and now returning to the original finite difference equation, we see that the second time step is here and everything else is on the first step. So given a initial condition, we can just plug in all of these, and this finite difference scheme will output this point. So manipulating this with some algebra, we can find that we can solve for u of I at the second time, at the n+1 time step, and that means this is an explicit. So to visualize it, we see we have like I-1, and then we have I, and then so we have I-1, I+1, and then all this is at the n time step, n+1. So all these terms are here, and we solve for the next time. So therefore, this is an explicit scheme. Thank you.